the amount units of energy. Energy form energy. Kinetic context of the to do work. Some truck that speed is that train truck just sitting there at rest. The amount of work is 1 feet squared. Exactly here and back. So, get the done on back that the energy the very make good sense to the I have the capable of going of doing life and on the speed it depends on the speed work to do that if it's going as fast it can do just where did look back at the EV, which gave one has there were lots of arguments in Newton's time about what is the pressure that they call the amount of weird in an object. That momentum. So the proponents of and the proponents at that time they realized both are useful in a way. They really back and forth what the that and and two different points of view are useful in their own way. An object moving to one gravitational energy is capable of doing some work something like that. where the of tallness. I'm not talking tallness, I'm how high age. Here's the other. That's what. And these to we that last week. That's how my work is capable of doing because and age are reasonable on the expression. Sure. My work and object is capable of doing age. Gravitational energy, you can go around. Here, calculated earlier in different contexts when we were talking about and thinking of the energy as an amount of work. What is about the amount of work system is capable of doing? Spring capacity do work on account of being extended or compressed. If it's extended out, it can do some work for me. If it's extended, it can. So, and do you remember what formula for that is? The work I did it was the work it takes me to this thing to a certain extent, but it's also the amount of work is capable in the back on the position. The formula squared, where x is the amount of position, in case the so-called free measures how. So the basic energy that we're going to be using for later on in the course of other ones, I'm going to call these for the moment control. For the sufficient reason that that's what the book calls them, mechanical forms of energy. But those are not the only forms of energy. They're just the ones that we're likely to encounter in discussion of mechanics. There's thermal energy. Thermal energy capacity to do work by virtue of high temperature. Shall I write the formula for you? It's not a formula we're ever going to be using in the course, but it happens to be the object of the mass of the substance times the absolute temperature of the substance. So you tell me how much stuff you've got, what kind of stuff it is, that tells you what the specific heat is, temperature is, and that will calculate for you the total amount of thermal energy that's contained in that substance. A hot object is capable of doing work for you that the same object cold is capable of doing. Does that make sense? Sure. You got a hot brick or something, you dump it in water runs a turbine, something like that, you generated electricity, whatever. I don't know. But a hot object is capable of doing work for you that that same object cold is not capable of doing for you. This is not a mechanical form of energy because, well, in a certain deep sense it is. What kind of energy is thermal energy? It's the random energy of all those molecules that went to make up the thing. So ultimately, it's also a kind of mechanical energy. But from the point of view of motion of gross objects like bricks or something, thermal energy is gone. It's invisible energy. I don't see it there. It just has how hot that brick is, not how that brick is moving, where it's located in the spring, how much that spring is stretched. Thermal energy does come indirectly into the subject of mechanics for the reason. Thermal energy is, in a way, the big garbage can of energy in the cosmos. Wherever energy started, it eventually winds up in the form of thermal energy. I sometimes think that thermal energy is the log to lawyers. As a fact, in society, wherever the money first came from, it winds up in the pocket of some lawyer. And thermal energy plays the same role in physics. After all the dust is settled and everything, where did that energy go to? Thermal energy. That's where it's eventually all headed. So from our point of view, thermal energy is just a great dump. Other forms, chemical energy. That would be the capacity to do work by virtue of chemical composition. For that, I can't give you a formula, but I'll give you an example. Dynamite. A stick of dynamite is capable of doing a lot of work for you that same, after it's exploded, same atoms and everything, is no longer capable of doing for you because the chemical bonds have been busted or something or other, and for that reason the thing is no longer capable of doing the work that it was originally capable of doing. So there's chemical energy, nuclear energy. Nuclear energy, that would be the capacity to do work by virtue of nuclear structure. Uranium, a lot of it. But after the uranium has radioactively integrated and produced a bunch of daughter nuclei, same stuff, but just rearranged, it's no longer capable of doing much work for you. That's nuclear energy, and obviously this could go on and on. What I'm trying to emphasize here is that there are many different forms that energy can take, of which we are mainly concerned with 3 and indirectly of 4. But in principle, there are all the other 2. These we call non-mechanical. From the point of view of bricks moving around and trains moving up and down, that's sort of invisible energy. Now, the importance of the concept of energy derives mainly from the following. The law of conservation of energy which says energy can be converted from one form to another, or it can be transferred from one object to another, but it can't be created or destroyed. Total is always the same after and before. An example of transfer of energy from one object to another.
Electricity.
Electricity, yes, would be okay, or a conversion of one form to another. Just the cleanest, most transfer of energy from one object to lighting. Billiard ball comes along, kinetic energy hits the other one takes off. Now this one's got the kinetic energy, and the first one is stopped still, at least if you hit it head on. So there's ball collision is an example of the transfer of kinetic energy from one object to another. Or it can be converted from one form to another. What's an example of converting energy from one form to another? So I have this here and I drop it. Right now it's got a lot of gravitational energy because it's up high. When it's just about to hit it doesn't have any gravitational energy because it's down ground level, but it's got a lot of kinetic energy. So there was conversion of energy from gravitational form now to kinetic form when it hits my foot. So rock, gravitational, converted into kinetic. Where's the sense? Energy is transferred from one object to another, converted from one form to another, but it can never be destroyed. The sum after the same as the I could write that formally as E final is equal to E initial in any process. I'm not going to prove that now for you, for the very good reason that it's not provable. Not provable from Newton's law of mechanics. It's almost provable for certain classes of forces, and I'll come to that on Wednesday. Sort of a subtle problem. What kinds of forces energy? We now believe, physicists since the mid-19th century, the law of conservation of energy is more deep and more general than Newton's laws of motion, and there are reasons for that, but derived from the conservation of energy general case, in its general form, as just stated, you're never going to be able to derive that from Newton's laws alone, which you can sort of derive it. I'll show you that, and then we'll see maybe what the ostensible are and what actually they're not genuine exceptions of the conservation of energy actually is always valid, even though not provable in Newton's laws. Well, that's an archaeological situation. Today, I'm just going to examples of conservation of energy to show you what's very important. Conservation of energy is almost always the fastest way. Doesn't the answer, but it is conservation of energy. That's that. Even if the problem was, well, conservation of energy is fantastically powerful. So let's do some examples. I'll do it a third time by conservation of energy. So of all conservation of energy, I drop a rock from a height 8. Going when it gets to the ground. Probably originally when I was talking about Newton's laws and laws of acceleration, we did try to using the work energy theorem, a more sophisticated way of the same problem. Now I'm going to analyze it from the point of view of conservation of energy. So in this situation, I drop the rock from up there, mass m, and the question is, how fast is it going if it's the ground down here? The initial energy, when it was up at the, you tell me, gravitational energy, released from rest. And it hit the bottom, before it hit the bottom, half squared, it's all kinetic now. Energy? No, because conservation test. That does not equal. Energy is the same energy. 1/2 v squared is equal to m. I see m squared. I multiply by 2. I get v squared equals 2gh, or if I take the square root of it, v is equal to gh. As I say, we've got that. What's going on here? Energy was converted from energy
So in this case, the energy can
Well, okay, so suppose that down here, for example, then I have 1/2 and the initial square, and therefore velocity with on the left-hand side, yes, 2 and almost a case where it was dropped, if it was dropped. Would be good by an ambiguity in the formula for gravitational. In the MH, because H is slightly above what? Height above the table, height of the sub. They told me. And doesn't matter. But if you stick with that, watch. Why? Because it turns out gravitational energy that every is independent. Exactly. Using a different it's down here. Only the change. Problem. Suppose that I had perversely measure height above the surface. How would that drawing look? Brick, on the table, but for some reason I a basement. So the basement. And we said that above the base. So I'm going to measure this point down here. Same argument as before. Initial is equal to G the height above the subbase. H plus. Initial gravitational when I do the problem over here. The final energy when I hit the floor. Kinetic energy. But it's also gravitational energy now because it's still evaporate, but I'm using so plus and see how it goes? So I know still got some residual gravitational energy, capital H, because it's still up there above the basement, not above the floor. So I use conservation of energy. Is equal to E initial V squared plus mg capital H is equal to the initial energy and little h plus mg capital H capital H cancels out. And I'm right back to the equation, 1/2 v squared equals mgh. What I had over here, and the thing is the final velocity. Do you see what that is? It's only the change in height that ever matters. If you change the reference, switching it to the subbasement or something like that, the initial gravitational energy will also increase the final gravitational energy, and by the same amount, so by conservation of energy, it's going to cancel out on the two sides. The only time that you can get into serious trouble with this sort of thing is if you inadvertently use this as your reference point for the beginning of the problem, and this is your reference point for the end of the problem. Then you've been inconsistent, and your answer is going to come out wrong. But as long as you decide at the beginning of the problem, this is where I measure my heights from, and stick to that, you'll be okay. I usually scan the problem, find out where the thing is actually going to land, like is it heading for the floor, or is it a hole in the floor, and it's literally going down to the subbasement or something, find out where it's planning to go, and use that as my reference. Okay, so there's an ambiguity in gravitational energy. A little bit more example now. I come back to the roller coaster problem that I suggested last Friday in the context of the work energy theorem. That was actually a kind of cumbersome way of thinking about it. Now I want to do the same kind of problem using conservation of energy. Beautifully clean. Here's the roller coaster. And the roller coaster starts from rest up here. Do I need to say frictionless? It starts from rest at point A, which is up on a tower that's actually 20 meters up. It comes down to point B, whoops, and then goes up to point C, which it happens is 15 meters up. It's about the ground. That was supposed to be a nice horizontal line there. Question: how fast is this thing going when it reaches point B? And then how fast is it going when it reaches point C? Ready? Well, I write down the initial energy. That's the energy at point A. What was that? Kinetic energy? Nope. I said it started from rest. No kinetic energy. Gravitational energy? Yes. What is it? mgh. What should we measure our h above? I think the ground level is the sensible one to do in this case, so it's mgh. That would be the mass of this thing, which, by the way, they never told me, but this time it's not going to matter. Times g, that's 10, close enough for me, times h, that was 20 meters, so this is going to be 200 times the mass, whatever that mass is. That's the energy that this thing started out with. That's what we've got to play with. Okay, how about at point B? What form is the energy when it reaches point B? All kinetic, because it's down at ground level. The height is 0 now. Got no gravitational energy. It's all kinetic, so it's 1/2 mv. I'm going to say v sub b squared because I don't want you to confuse that with the velocity that it has later on at point C. So kinetic only, huh? We've got pure conversion of energy from gravitational to kinetic. Conservation of energy says that those two must be equal, so 1/2 mv VB squared is equal to 200 m. The m's conveniently cancel out. I multiply through by a 2. VB squared is equal to 400. Ah, how nice. VB is I
20.
lost you. Square root of 400 is 20. Huh? So that's the velocity at point B. By the way, I didn't even know a thing about the shape of the track in between. I never told you what this shape was. It seemed to be going generally. Well, I did need to know one thing. I needed to know that the track did not secretly go like that, right? If it had done that, then the roller coaster would have ridden up to there and it would have run out of energy and then it would have sloshed back and forth. So it would be rocking back and forth in that little dip. So I do have to know that it at least made it to point B. So there was no point on the track that was actually higher than point A. But apart from that, I don't need to know a thing about it. Doesn't matter what the shape is. It fell a total distance of 20 meters, and therefore, when it got to the bottom, it is going at 20 meters per second. Could have dropped straight down for all.
You also have to know that the slope at A is 0 or negative. Because if it's a
Oh, otherwise it wouldn't go.
you would go the
Okay,
wrong direction.
very good. And the slope is 0, and I just breathed on it ever so slightly to get the thing going. Yeah,
You
you're right.
sketched it that way, but it wasn't stated.
Good point. So, okay, how about C? That's the one I really wanted to do this problem for. What's the energy at C? Here, it's got gravitational energy. It's also got some kinetic energy. So it's got both. 1/2 mvc squared is the kinetic energy it has at that point. And it also has gravitational energy, mg times the height that it is there, which is 15. So, conservation of energy says if I compare the beginning and the end, or I can compare the middle and the end if I care to, but I've got a nice formula for the total energy at point A. It's 200 m has got to be equal to 1/2 mvc squared plus m times g, which is 10, times h, which is 15, so that would be a total of 150. Again, the m's cancel all the way through. I subtract the 50 over to the other side. 200 minus 150 is 50, is equal to 1/2 mvc squared. By the I get vc squared is equal to 100, and therefore V at point C, the square root of that, 10 meters per second. See how easy this is? If you wanted to know, this track can go on for forever, as far as I'm concerned, as long as there's no frictional losses in here. At any point, you tell me how high that point is above the ground level, and I'll figure out what the velocity is at that point. Conservation of energy. Let me show you a cute example of that. A famous problem. Not unlike the loop problem that you'll encounter on the next towel. This is the igloo problem. Example 3. Imagine that you had some kid who's sitting on the top of a igloo. Igloo is made out of ice, so it's frictionless, and they're hemispherical. Always made them that way. So here's the kid, kind of cubical. He's sitting on the top. He begins to slide off because somebody breathed on him from the back, or gave him a little shove, and he starts to slide off. And at some point, as he goes down here, he actually leaves the surface and flies off. And the question is, at what angle does he actually leave the surface? You have a picture of that? So he's sliding down here, going faster and faster, and pretty soon he takes off, leaves the surface completely. I want to know, at what angle does he leave that surface? Let's say that the igloo has a radius r. So there's the question. Solution. First of all, let's figure out how fast he's going when he gets to angle theta. Let's say that this is a height h up above the ground. Then how fast is he going? That I can get by conservation of energy. E initial, when he was up at the top, measuring gravitational energy, as seems reasonable from ground level. Well, you tell me, what was his gravitational energy at the top when he just started? mgr, huh? Kinetic energy? Zip, that was at rest. Final energy, that's at the moment that he loses contact with the surface. That's the final point. That would be, first of all, he's got kinetic energy, 1/2 v squared. But he's also got some gravitational energy at that point, mgh. So far, so good. What h is? That's what I'm trying to find out, actually. Let's write it in terms of theta, because they said get h. Our sine. This is energy. M cancels all the way through. Why don't I pull this GR over to the other side and write this equation just as well as 1/2 v squared is equal to GR times 1 minus sine theta. Or I'm going to tidy this up. What I'm really interested in is v. V squared is equal to 2GR times 1 minus sine of theta. That certainly is true by conservation of energy. When he flies off, his velocity is going to be 2GR times 1 minus sine theta, whatever that theta is. Now, we have to think for a moment. What is the criterion that he just flies off? A very subtle point, but there's a whole class of problems of this type. Let me draw a force diagram for this guy. In general, what forces act on him? I'm enlarging him somewhat so we can see it better. What forces are acting on him as he slides down the ice there? What would you say? Gravity. Gravity for sure. mg. What else? Normal force. Very good. Perpendicular to the surface. There it is. Now he has two kinds of acceleration here. Because of the tangential component of mg, he's actually speeding up as he goes down, of course. But in addition, because he's going in a circle, he's got centripetal acceleration in toward the center. So in toward the center, if I peel off the component, the radial component of mg, I have mg. Now I've done exactly what I told you never to do. Drawn an angle that's close to 45 degrees, so I don't know whether this is theta or this is theta. I'm going to use my trick. If they're perpendicular right side of this one, to right side, whoops, right side of this one to right side of this one down here, and left side of this one to left side of this one. This is the angle theta down there. So mg sine of theta is the, I wouldn't have had to do that if I'd drawn a diagram where that theta was very clearly not close to 45 degrees. Then I could have told you the diagram. mg sine of theta, pulling in toward the center, minus n is equal to m, the mass times its acceleration, which is v squared over r, because it's going in a circle. There's the centripetal part of the equation. M cos theta, well, but that's the problem. It was great. Now you tell me, what is moment the surface at that point is getting smaller until the surface. When he leaves the surface is the moment when n hits 0. At that point you can slide a piece of tissue paper under him and he's not going to crumple it because he's not touching anymore. No normal force acting from the surface. Well, m's cancel and I get g, well, might as well multiply through by the r, gr sine theta is equal to v squared. So there's the condition that he's just barely sliding off. Here's the condition for his velocity at any angle theta from conservation of energy. Let me put those two together. There are two formulas for v squared, if you like. R g sine of theta is equal to v squared, which is 2rg times 1 minus sine of theta. Rg cancels, and I get sine of theta is equal to 2 minus 2 sine of theta, or pulling a 2 sine theta over here, I've got 3 sine theta equals 2, or sine theta is equal to 2/3. How about that? 2/3. So 2 divided by 3 equals 0.67. No surprise. I want the arc sine of that. It's 41.8 degrees. Turns out not. There you are. That's the angle. Second equation, the realistic point of fact down to set up here and then have time to wrong math. Don't look at what's happening now. Something very peculiar. You see it? People who are up close. This thing is spinning like crazy.
Yeah.
Now it's spinning less again. Now it's starting to spin more. It's actually converting spring energy, kinetic energy, gravitational energy, or all of them